Welcome everybody to this afternoon's session in the ecosystem track. My name is Dan Powers. I work at Docker doing and running the partner technology integration team. Today we have two very important partners in the Docker ecosystem, StorageOS and Dynatrace. And at first we'll hear from Alex Chircop on cloud-native storage partners, and then from Alois Meyer on making application monitoring a cloud-native platform feature. I'd ask you all to, if there's questions at the end, to see if you can make your way to one of these microphones that are across. If you happen to be sitting in the middle and you can't do the gymnastics to get out of your seat, just tell us so and they'll repeat your question for you. Anyway, please welcome Alex.
Good afternoon. So my name is Alex Chircop, and I'm the CTO and one of the founders of StorageOS. And I'm here to talk a bit about cloud-native storage patterns, which is basically how you can use different storage solutions in your microservices and in your Docker platform. So containers have obviously changed the way we deploy apps to our infrastructure. We've kind of gone from VMware doing optimization of hardware to containers doing optimization of how you develop and deploy and manage the configuration of those applications. But you're a DockerCon, so I guess you already knew this. So very, very quickly, as a problem statement, Docker uses a function of layers to define how the images run. And an application can be made up of a number of different layers, and this obviously helps reduce the size of the overall images. On top of that, on top of those images, we have a single copy on write overlay. And what this allows you to do is to have a temporary working space that your container uses to run. Obviously, the downside to all of this is that once an app is terminated, your data goes. So fundamentally, containers were originally designed to be stateless. They don't have data persistence. They cannot maintain data when they're either moved to another node or the container is destroyed. But why is this important? Why do you need storage? Well, fundamentally, there's no such thing as a stateless architecture, clearly. State in your application is stored somewhere. It could be in databases. It could be in object stores or something like that. But ultimately, what most enterprises start to grapple with as they mature their container environment or their orchestration environment is that they've moved some of the easy stuff, they've moved some of the stateless stuff into this environment, and now want to consider how they work with storage systems. So why is storage critical? Clearly, things like application binaries, those are ephemeral. They just need performance storage, but they don't actually need to have state other than what you already have from your registry or your DTRs. But application data, so things like databases, message queues, instrumentation, those sort of things need dedicated persistent storage. And it's not just any persistent storage. It needs storage that can be performant. So for example, you need different types of storage, like block storage for databases. You might need storage replication features to enable high availability, depending on what your storage patterns are. And you probably also need things like snapshots for point-in-time copies, or to help with your CI/CD environment, and encryption to secure data in the cloud. Things like configuration or other reference data that your applications might use might definitely benefit from having things like shared file systems, which you can share across a number of nodes. And obviously for backups, you also need to think about compression and deduplication and how you do that to the cloud. So there are a bunch of different options, and a lot of the initial stateless microarchitectures might be using things like object stores or other time series databases somewhere else in the system. But ultimately, many applications, and in fact, most applications, need some sort of storage that results in storing data to some sort of volume, which typically sits on some sort of file system or some sort of block device within the environment. So I'm going to talk a little bit. We spent some time defining what we thought were the important principles that would apply to cloud-native storage. And these are some of the things you can take away to kind of use as a yardstick to measure how different storage options compare in your environment. So first off, though, what is cloud-native? Cloud-native is something that is defined by, I guess, the container and the Docker environment and the orchestration. Something that's horizontally scalable, no single points of failure, which means that it's resilient and survivable across software failures or hardware failures. Obviously, you want all of this environment to be composable and declarative, so you minimize overhead by automation. And fundamentally, you don't want to be tied into any particular platform. The whole beauty of something like Docker is, and Kubernetes now, is that you have an abstraction layer from the underlying infrastructure. So what do we think are those 8 principles for cloud-native storage? Well, for the longest time, storage has always been presented to operating system instances or to hypervisors. We think if you're looking at application storage, you need to evaluate how application-centric the storage is. We think storage should be presented to applications because at the end of the day, it's the applications that are consuming those volumes. Of course, you want your applications to run everywhere. That means that you're probably looking at software options which allow you to have a platform-agnostic way of deploying this. Most organizations might have a mix of multiple different hardware or virtualization platforms or different cloud providers that they need to work with. And you want your storage environment to work in all of those environments. Of course, you want your storage to be composable. Just in the same way as you define a Kubernetes pod or a Docker services file, you want to be able to say, not just this is what my application depends on in terms of CPU and memory, but you also want to say, these are the volumes it depends on, and these are the attributes of my storage. And for it to be composable, it has to be API-driven. So there's no point looking at storage options that maybe have static provisioning, they don't support API-driven environments, or maybe they use CLIs, because really containers need to start up quickly and they need to get their access to their storage quickly. We think that there are a whole suite of different options, like object stores, which are particularly good at storing mass data and large chunks of data. However, there are lots of transactional systems, and for transactional systems, you want to make sure that your storage has some sort of deterministic performance. And what we mean by that is that it allows you to operate in a predetermined way and doesn't suddenly change its performance characteristics based on failure modes or other things that are happening within the infrastructure environment. We also think that storage is one of those layers that you just need to depend on. It has to be consistently available. So non-disruptive operations within the storage environment are absolutely key. The other big thing, and obviously this is pushed continually by Docker, is you really want your microservices environment to be natively secure. So in much the same way that you control the types of images that are deployed and who can deploy them and who can run applications, you also want to maintain the same thing across different namespaces and different role-space mechanisms when you're accessing your data volumes. And finally, you want that basic agility. You want the ability to move volumes about, have data mobility, be able to resize volumes, and have all the sort of things that you would expect out of a normal storage system in your enterprise. So, how do enterprise benefit from all of this? One of the key things is obviously storage mobility. Once you have a storage system that can be orchestrated with an API, you can have end-to-end movement of not just your application, but also all the other dependencies of your application, like your storage. Persistent data means that you can now have a container that uses a volume. That container can move around different nodes in the cluster, or indeed can move around perhaps different platforms altogether, and continue to access the same volume just like the data was local. Obviously, once you get to the point where you have schedulers and orchestrators, you can also then consider more advanced scheduling features like hotspots. So, for example, you need to upgrade the performance of your application. You need to move your application to a faster node. You can do all of those things dynamically now. And obviously, you get all the benefits of a software-defined system, so you can now deploy the environment everywhere within your infrastructure. And what this gives you is one of the key benefits of that mobility is business continuity in HA. So lots and lots of storage, lots and lots of application patterns have some sort of dependency of your storage being available across different nodes, either for high availability purposes or for business continuity, where, for example, you're using storage level replication to replicate across different availability zones or different data centers or different racks within a data center, for example. And this gives you the ability to quickly recover your applications and your databases, etc. So how does Docker persistent storage work? Well, initially, it was really, really simple. It was just mounting an individual directory from the host system, which wasn't particularly great because the host system was non-portable. So you were referring to a directory which wouldn't work across other nodes. So the next step, the next evolution was the so-called named volumes. And this added a big benefit because now your volumes were referenceable, and you could compose them into your services file or your Kubernetes pods or whatever. So now you could refer to a volume, and that volume would be something that would be an abstraction layer that names an abstraction to the actual place on disk where it actually lived. And then the next evolution was volume plugins. So volume plugins give Docker the ability to automatically reach out to external storage providers and integrate them into the same infrastructure that named volumes use within standard containers. So a Docker volume plugin is integrated into Docker. You can just they're a fundamental part of Docker from 1.10 onwards. It effectively extends the ecosystem to allow you to use external storage providers. There are dozens of different plugins available. Obviously, once you have an externalized storage provider, you get the ability to persist the data beyond the life of the host because the data is no longer tied to just an individual host. And you can actually choose from different environments. So you can choose from different storage presentations like block or file or object, depending on what you actually need. One of the nice things about using the Docker volume plugin is that you can continue to use the standard Docker volume commands that you were using previously. The only difference is that you specify the ---- driver option to specify which plugin you're going to use. So automatically, you have the ability now to create, delete, list, mount volumes into the different namespaces based on just that volume name. So as a real-world example, we have StorageOS. This is my little plug, where we have a single container that includes both the data plane, which manages the data path for a volume, and the control plane, which manages the cluster health, the config, and the policy for different volumes, and has all the API endpoints to integrate natively into the Docker plugin ecosystem as well into Kubernetes. So a Docker volume plugin gives you all the API endpoints for Docker volume operations. So you have an API between the Docker engine and the external provider to do things like create, mount, delete. The plugins are available from the Docker store. Last count, I think there's about 20 of them. And what this allows you to do is it allows the plugin to actually say, dynamically create or to mount a volume, which then the Docker engine uses to integrate into the Docker namespace natively. So you can mount one or more volumes and specify the path where you want those volumes mounted within the container, and those volumes now become part of the container namespace. As a very simple example, you can install plugins through the Docker plugin command. So Docker plugin install and the path to the Docker hub or the Docker store. You tend to give it an alias. The alias just simplifies the install, so you can use perhaps a more friendly name than the whole path of the plugin for future references. And it's kind of like installing a driver. So once you go to install a plugin, it asks you whether you want to accept the sort of privileges that the plugin requires to run on that environment. If you have large clusters, you obviously have to install the plugin across every node in your environment. The plugins have to be installed in basically every cluster node that actually is going to use the storage. If you're using Docker plugins, you also gain all of the benefits of using the external storage volumes within Docker Swarm as well. And you can define those. You can now use service definitions to define how you use those volumes within Swarm. And obviously, other schedulers have different ways of integrating drivers, including native drivers that are sort of mainlined into Kubernetes, which you gain the advantage of now with the new Kubernetes for Docker environment. And there are also external APIs to allow you to extend that further. As a little example, this example on the screen here shows you, for example, how you can use a Docker Volume plugin to create a highly available WordPress. So this is really quite a simple example, but you have two services. The first service is a database, which uses an external volume driver. You can see that the volume driver there specified is StorageOS, and it's mounting a volume name into varlib MySQL. And what that does is it allows you to create a MySQL instance, which Swarm can schedule on one of the nodes within your cluster. And it gives you a highly available system. So if your MySQL instance dies, it can transparently move to one of the other nodes in the cluster. And the Docker Swarm will transparently do that for you. And on the flip side, you have then another service definition, which actually configures the front-end service, the actual WordPress service that's consuming the database on the back end. So this is a very simple example of what you can do when you have highly available databases that you've now enabled using a highly available storage layer. One thing to remember is that with an orchestrator like Kubernetes, the orchestrator will have an interface to manage the storage system and how volumes map to applications. So if you're using Kubernetes to manage the mounts, then you probably don't necessarily need the Docker plugin. Not all plugins are simple. So some plugins are API frameworks that provide a translation, that are only providing a translation layer between the Docker interface and the actual external storage system. There are obviously many options for storage. And just because there's a plugin for a storage doesn't necessarily mean it supports all of the services that you might expect out of your Docker environment. For example, some legacy storage systems might not support things like dynamic provisioning or the ability to create volumes on the fly or to be able to move volumes easily across nodes. And in fact, some of the storage systems out there only do pre-provisioned volumes, which obviously doesn't give you the benefits that you might need when you define volume state in a composable manner. However, there's a really diverse ecosystem. There are tons of plugins, lots of different interfaces, and lots of different frameworks. The good news is that both the CNCF and the different orchestrator platforms are working together and have created a new standard called CSI, the Container Storage Interface. And this storage interface aims to standardize the methods where storage orchestrators can talk to individual different storage systems. I was going to do a little demo, but the clock is showing 44 seconds. So I'm just going to switch to the questions, but if anybody wants to see a demo, I'm happy to do a demo outside or at our stand if you'd like to follow up in any more detail.